This is one of the talks of the series of the HeapLab talks, and today we have Stephan Ploegers. We'll talk about data flow analysis and a work we are carrying on together about how can you use data flow analysis to detect functional interfaces, so arguments, return values, and these kind of things. So without further ado, let's thank our speaker for being here. Stephan.
Okay, thank you, Andrew. I'm a worker on the Fraunhofer FKI Institute, which is actually a research center. But that's, well, not my real main profession. I'm actually a PhD student at the University of Bonn in the group of Professor Matthew Smith. The group is actually working on usable security and privacy, but my main part of work is more like the binary analysis, and in that case we are actually trying to recognize function interfaces, and well, that's what I'm talking about, what it is trying. So the motivation for that is the data flow analysis or the monotone framework theory can be used mostly in compilers for binary analysis. It is like a very connected field in a certain way because you try to use optimizations to get information in code or to reduce like the code as in compilers. In the binary analysis, it is oftentimes used to as a part for things like liveness analysis to see at a certain point variables are usable or not, as well as things like trying to figure out if you can drop a value through the control flow graph and to the end and see if it's used or not used. Data flow analysis is a technique for gathering information about a possible set of values calculated at various points in the program. So various points means that you not only want to have like the value of a variable at the beginning or the end, but sometimes it's even, most of the time, it's also interesting to see so what is in between, in the steps between, and the actual values are not like values like the 1, 2, 3, or is it like is the variable 5, is it 6 or whatever, but also things like is it alive, is it not alive. Can you use it, can you not use it? So the meaning of value is not like only it's a number, but it can be also different things. Data flow analysis is usually used as a static analysis. So the program you're trying to analyze is not executed, which has of course the typical pros and cons. It is based on the control flow graph. You see later on some examples of the control flow graph. And there's an interprocedural part, so which is like the connections between functions, and there's the interprocedural part, which is like the analysis inside of the function. Today I will most of the time talk about the intraprocedural part, and just talk a little bit about the interprocedural part. So a monotone framework is actually just a framework to generalize data flow analysis. So you just have like a bunch of rules, and with these rules you can actually use, do a data flow analysis. So yes, a way of generalization that you can reuse the framework in different scenarios and still be fine. So let's jump right into an example. We have an example function called ex, and it has actually an argument and a local variable called a. It's pretty simple. We have like an if-else block. In the if block, the variable a is set to 1, and in the else block it is set to 3, and later on it's returned. On the right side, you can see the corresponding control flow graph of the function, which is like 4 blocks. With the starting block, the initialization, the if and else part, and later on the combination of both when you return the whole thing. So what we now want to do is we want to try to determine what kind of values in the meaning of what kind of real numbers actually the variable a can have in this very small function. To do so, we of course need to have like a set of values, so a set of possibilities that a can have. In this case, you can see, okay, a can have the values 1 and 3, but let's assume that also 2 might be a possibility, and have our set of values is like 1, 2, 3. In usual programs, of course, you have like the natural numbers or anything like that, you know, the numbers between 2 to the power of 32 or 46, whatever thing you have. It might look a bit strange why we choose the set of values as 1, 2, 3, but later on we will see that this is actually the meaning in a way. Okay, so we start at the beginning, from the top, and at the top we don't know what the initial value of a is. So a is like the empty set. And now we try to analyze the instructions and get information out of the instructions. And to do so, we need a so-called transfer function. The transfer function just takes as an input the current solution, which is at the top like the empty set, and also an instruction, and tries to get information out of it. And if you go through the first block at the top, you will see, okay, I don't get any information about the actual value because it's just initialized, and that's it. Then you take the left part and the right part, and actually in every of the both parts you get information. You also apply the transfer function to the part and to the solution. The solution at the end of the first block is the empty set, so it's also the solution at the beginning of the set, the left and right block. You apply the transfer function, and after the left block you know, okay, a can be 1, and if you apply the things to the right block, you know, okay, a can be 3. And at that point, both paths, the left and the right one, are met again, and at that point you need a combination operator. You need to combine the two actual values that the variable a can have at that moment, and you need to combine them to say, okay, at the start of the last block, a can be 1 or a can be 3. And you again apply the transfer function to the last block, which is only containing the return instruction. You get no further information, so at the bottom of the whole function, a can have the values 1 and 3. So what we now have is like a set of solutions. And in the scenario before, you could see that a could have the solution 1 or 3, so the set was 1, 3. But it might also be possible, since we have like the set of value contains 1, 2, and 3, that you might have other solutions for a in other functions. And you get something that looks like this. You have the empty set, so you might have a solution where, well, a has actually no value, or you can have like the value 1, 2, 3, or any combination of the values 1, 2, or 3. In that case, this actually the power set of the underlying values, but it's not necessary in every like monotone framework. It's just the thing in this example. So you have the set of solution, the transfer function you apply to the solution and the instructions or blocks. You have the combination operator, which actually takes two solutions and gives you the combination of both. And the combination operator actually induces a so-called partial ordering, which is a relation. And this relation can be used to say that you have like more information or less information. It gives you like an ordering of the solutions. In that case, if you start from the bottom, you see the edges, and there's an edge from the empty set to 1. So in that case, this is a relation, which is the subset relation, and you know, okay, the set that contains 1 is a superset of the empty set, and if you follow these edges, you also have like, yeah, the actual partial orderings, the relations. you can combine the set of solutions with the partial ordering, which is called a lattice. So this thing is actually a lotted lattice, and you have still, of course, have the combination operator and the transfer function, but there's also one very important thing. You need to satisfy the so-called ascending chain condition. Okay, so the ascending chain condition is a quite simple thing. A chain is like a form of ordering. So a chain would be like the empty set 2, 1, 2, 1, 2, 2, 1, 2, 3, because they are all like in a chain by the partial ordering. And that might look something like this. You start from like a point and you go upwards, ascending through the chain, and there's the important factor is that this chain has a finite height. So it's not like infinite length, because if you have like an analysis and you have like an infinite chain, what can happen is you have a loop and you always go through the loop again and again and again, and since you never reach the end of this chain, you're actually stuck in it, so your analysis will never end. So in summary, a monotone framework needs 3 important things. It needs a lattice, which contains the set of solutions and the partial ordering. It needs a combination operator, which satisfies the expanding chain rule, and it needs a so-called transfer function to be able to apply, or to get information out of the actual instructions you are working with. Okay, so now the question what I'm doing with this framework. And what you want to do is you want to get information about the whole function. So on the left side you can see a control flow graph with 4 blocks A, B, C, and D. And you want to have solutions for every part of the actual function. So for the top of each block, and in this case for the top and the bottom of each block. So you get equations. At the entry you have an initialization, and after you apply the transfer function to the top of the block A, you get the solution for the exit of block A, which is the exit. So an exit is nothing else than the transfer function applied to the entry of the block. And you follow the control flow through the edges, and you can see that B entry is actually the combination of the exit of the predecessor, or of both predecessors, because there's a loop from B. You have 2 predecessors. Actually, B is the predecessor of itself, as well as A is the predecessor of B. So we have the combination of A exit and B exit, which is the entry. And you do that all the way down, so you get for every block and every position in the block, you get an equation, and now is the problem to solve these equations to get a solution for everything. We did that more or less by hand during the example, but you need, of course, an algorithm, and there are, well, technically a lot of algorithms that can solve these kinds of equations, but there is one which is most of the time used, which is the MFP solution. It's called maximal fixed point. You can also say least fixed point. It's depending on the point of view, but it's not a very important factor. The algorithm works as well. We have the solutions, which are the main thing, the data flow analysis. You have a so-called working list. You initialize them. You want, of course, the equations for all the different parts. So you take all the edges in the working list. And now you work on the working list. And you try to work every edge after another. And you get, as you can see in the right part of this slide, you take the first part of the first solution of the edge, which is actually S. You apply the transfer function, and you get the exit of the block, which is f of s. And if f of s is a gives you new information about that thing. That means that it's not in relation to the actual solution next to the block. You need to adjust your analysis because you have new information, and in that case you need to take all the next edges which are coming next from this block, and you need to put them all into the working list again, and yeah, you do this until you, well, hopefully have an empty working list. So what you need to do, of course, here is to make sure that the working list well, does not like, or is getting empty. If it's not empty, you have a problem, and in that case, it is very important that you have the relation as well as the combination operator to make sure that they satisfy, for example, the ascending chain rule. Otherwise, you wouldn't come to an end and like go to an infinity. Okay, so now let's go to an example, which is also the algorithm we are right now working on, which is the function interface recognition. There are some assumptions and givens. The first assumption is that no static argument is accessed indirectly. This is like an assumption to make sure that the possibilities of solution is not getting out of hand. If you not take this assumption, it's going to be very unpleasant. It's also an assumption that there's no dead code. I would say usually in normal programs you won't have dead code, but of course in things like malware there is a good chance to have dead code to make sure that the analysis of the actual malware is not that easy, but there are some other algorithms that eliminate dead code, and so you assume no dead code. We have also some givens, which are actually given by another data flow analysis or by another monotone framework. We have the function bodies, so we know the actual functions, and we know if a register is used in the terms of if it's written to, or if it's read from, if it's unused, or if it's co-safe inside of a function. Co-safe means that you usually push it on the stack at the beginning of the function, do some stuff with it inside the function, and later on put the actual value that you have pushed to the stack back in the register. So the value in the register at the beginning of the function and at the end of the function are the same. It's like, yeah, you save it for the caller. And with that in mind, the idea, or the main idea behind function interface recognition is that you can look at the function interfaces from two different points. You can look from it at the function level. So the function in this little example on the right side, the function f, you can like investigate what are the arguments of f if you look at the instructions of f. And the same holds not only for the argument but also for the return values. You can think about it and check all the instructions and say, well, maybe that's an argument or a return value of f. But you can also look at the calls to a function. In the scenario, or in the example, the function g is called, so maybe you get also information about function g because you call it inside of f and you might have some information about it. So we have a monotone framework, so we need a lattice. And we not only need one lattice, but we need at least 4 of them. One lattice for the arguments of the current function, so you want the point of view of the current function, you have a lattice for it. You want the return values of the current function, you also need a lattice for it. You have the arguments of the function calls inside the current function, and you also want the return values of the function calls. So you have like 4 lattices, and later on you combine them. Okay, so now we're inside a function. And we want to know, or we want to get the information, what are the arguments of this function. And the simplest idea about it is, if an element is read before it's written to, it's an argument. On the right side, you have the example, it's the function f, and the element ebx is read, and the element eax is written to. So ebx is an argument because the information that is inside of ebx is most likely from outside of the function, because nobody in the function is written to ebx, and therefore ebx is an argument. This is not that simple, that's the problem. So we need to adjust our letters, and we don't not only have like no and yes, but we have also things like maybe, undecidable, and of course a contradiction if something went wrong. You can also see here the combination operator included. The combination of two things is always like the edges that are, or you can follow the edges to the next shared point. So if you want to, let's say, combine a no with a maybe, you get a contradiction, because it's the next element in the following part. If you want to combine, let's say, undecidable and yes, you get a yes, because well, yes is in the way of undecidable and yes is in the way of yes. So here you can also see the implicitly the combination operator. Okay, we need also a transfer function. And first of all, there was the algorithm, the MFP, and in the MFP there was an initialization phase, and we also have, of course, an initialization. And there is a more or less standard initialization. We say that an element like a register or a stack slot in the assembly is not an argument if it's a saved register. A saved register, as a reminder, is a thing where the actual value is pushed to the stack, things are done and later on popped from the stack, and it has to be the same value at the beginning and at the end of the function. So initial states is no in the case of saved registers, and maybe you have no idea if it's not a saved register. So from that point on, you say, okay, I'm in the state of maybe, and I apply the transfer function, I get a yes if I read that variable. That's the same thing as you can see here. ebx is at the start of maybe, it's read from, so it goes from maybe to the state yes, because it's read. And if you write to it, well, you say, you can't really tell what it is now, it's undecidable, because technically it can be like an argument that is not used in the function, and the same holds for if I call another function and write to it, or I have a so-called unknown function call. An unknown function call is a call to a function. I have no clue what the function is. I mean, it is possible in the analysis that I have a function call and I don't know what the target of the function call is. So in that case, we take the safe route and say undecidable. And in NP, otherwise, always keep the state if you don't know what to do. So let's try a small example. We have two variables, and we want to know if these variables are actually arguments from the function point of view. So we start in line 1, we have eax and ebx, and we say maybe that's the initialization, maybe. We get to the line 2, and in line 2 we see, okay, eax is written to. The transfer function says, okay, eax is, in that case, most likely not an argument, but it can be an unused argument, therefore we can't decide it and say, okay, eax is undecidable. But ebx is actually read from, and the value is written to eax. So ebx is in the state of maybe at the beginning, in line 2, we read from it, it goes to the state yes. We get to the line 3, nothing changes, and at the end of the function, our conclusion is that eax it's undecidable, we don't know if it's a return value, an argument, but we are sure that EBX is actually an argument. Okay, so now let's get to the return values, also from the function point of view. The same, quite simple example. The overall simple idea is if I write a value to a variable and I don't use it until the function ends, it is a return value, because otherwise it is dead code. Okay, and that's the case on the right side. We write EBX to EAX. EAX is not used until the end of the function, so we say, okay, EAX is a return value. That's also not that simple, so we again have a slightly different lattice. We also have a maybe with only a yes or no, and also the safety point, the contradiction. So we have the transfer function, and we have the initialization, which is again no in the case of the safe register. Safe registers are a bad thing, we say always no. And we have maybe if it's not a safe register, so at the start of this function, everything might be a return value. We will see in the next parts. So if we are in the state of maybe and we write to it, we say, yeah, that's a return value. And we stay in that until we read again from it, and in that case, we are not quite sure. Is it really a return value? I mean, it still could be, but it's unlikely because it is used inside of the function, and therefore it might not be a return value, so we say it's a maybe. The same goes for the thing when you call a function and you do stuff with the variable there, like reading or writing it, or if you have the unknown call, if you don't know what's happening, you say, yeah, maybe, be on the safe track. And as always, if otherwise, keep in the state. So let's make an example. On the left side we have the function f, and we have two variables. We want to know, okay, are these variables return values? And we start with the initial values, which is maybe. We set in line 2 EAX to 5, so we write into it, and if we write to something, we say, yeah, that's good, it might be return value, let's put it to yes. We get to line 3, we write to EBX, and EAX is still not used, so we say, great, EAX and EBX are potential return values. We get to line 4, and in line 4 actually we use both of them, but we also write to EBX, so we say, okay, we use EAX, it's going back to maybe, we're not sure about it, but EBX is still written to, so we say yes, great, we reach the return, nothing changes, and our conclusion is that EAX might be a return value and EBX is a return value. Okay, so this was the point of view from the function itself. Now we get the point of view from the function calls. We go straight to the arguments. The idea is if we write to a variable and we don't use it until the call is reached, we assume that this is actually an argument of the call. So you can see that in the right example, we write to EAX, and EAX is not used again until the call is reached. Therefore, we assume, okay, EAX is an argument option. It's also not that simple. And now we have like a tuple of states. And it might be a bit well, strange, but you will later on see why we need that in the next upcoming example. You have the lattice again, and of course, you have the implied combination operator. We have like maybe, yes, maybe, or everything yes, and we will now see why we need that. We have the transfer function, and I think this is interesting, but without the example hard to understand, so we just skip to the example. This is our function. And we have like 4 lines of code. We have a loop in the second block. And we start at the beginning, and it's always initialized with maybe, maybe. If not, if it's a saved register, that's not the case. Okay, so we initialize EX and EBX, the only variables, with maybe, maybe. And the first part is the state before the actual function call, and the second part is the state after the function call. And with the function call, I mean the function call you're actually looking at it, which is in this case the call to G. Okay, so we start with maybe, maybe for both the variables. We get to line 1, and we write into EAX. And as in the simple idea, we say, okay, if you write to something, that's good. If we now reach the call, we would say, yeah, that's an argument, great. So we say, okay, before the call, EAX is actually a yes. And we don't do anything with EBX, so it stays in the state. We get to the second line, and the second line says, okay, EBX is equals EAX. The thing is, right now, we are loading from EAX. So we assume that, yeah, we're not quite sure right now if it's actually an argument of the function call. So we go back from the yes state before the call to the maybe state. And EBX changes, because EBX right now is on the greatest hope. It is written to and not used again. So EAX is maybe, maybe, and EBX is yes, maybe. We get to the next block, into line 3, we call the actual function. And we know, okay, EBX was yes before the call, we called it, and therefore we know, okay, after the call, this is actually the real argument. We say EBX is a yes, and we put it on the right side, on the after call side. The thing is, about EAX, we are actually not quite sure about it, and therefore the state stays the same, and we say that's still a maybe. So we get to the line 4, and in line 4 things change, because we are actually also before the call, not only after the call, but before the call at the same time due to the loop, and we write something in EAX, and therefore it's going to be in the yes state to the before call part. And since we know that EBX is actually an argument of the function G, we just keep it in the state and do nothing. Therefore, we go back to the line 3 the second time. We know, okay, EAX is actually yes. Therefore, it's going to be a yes in the call, and we know, yeah, it's actually an argument. With EBX, nothing happens. We get our final information like 2-3 steps ago, and we go to the line 4 a second time. We know about both that they are actual arguments. So we finish there and say, great, EAX and EBX are actually arguments. They have the yes on the right side. Okay, last part, return values from the call of the function point of view. So we assume that the thing is a return value of a function call if there's a write inside of the function call and a read afterwards. Okay, so that's the simple idea. On the right side we see an example. We have in line 3 the call to the function G. In line 8, G sets the value ECX, so ECX is written to inside the function. We get back to line 4, which to the return, which is after the call, and we then read from ECX. So we assume, okay, ECX is set in the function, read afterwards, therefore this is a return value. This is the simple idea. We get letters, as well as the combination operator, of course, with different states again, and with the transfer function, you will see that we have again the saved register, not saved register initialization. Important is that it is the saved registers of the call function, not the actual function you're in right now. You say in the case of the saved register, no, it's not a return value, never. And in the case of a not saved register, you at first say it's undecidable. So you initialize them with undecidable because the important point when the actual analysis starts is when the call happens. Before the call, you know nothing about the return value of the call, so the actual analysis starts with the call. And if you reach the call, which is in the second line there, you go from undecidable to maybe if you write into it. So it's like the activation of the actual variable. You say, yeah, maybe it's a return value. And if you're actually in the state of maybe, and you read afterwards, you say, great, that's a return value. And if you write to it, you say, yeah, I'm not sure about it, I go to undecidable, which is also the case for the unfollowed normal function thing, which is like, yeah, better to be on the safe side, it's undecidable. So let's give a little bit of example. On the left side, we have the function f, and in the first line, you initialize the variables both with undecidable. You get to the second line, you have not reached the actual important call, so the no information are given. You just stay in this state of undecidable. In line 3, you reach the actual call. There's a write in EAX and EBX, so they get activated. So both are in the state main. You return from the call G, and you get to the line 4, and in the line 4 you see, okay, EBX is read from, therefore it's actually an argument, so you go in the state yes, and EAX is written to, so you have no clue what about EAX, so you go into the state undecidable, you go to the return state, nothing changes, and the conclusion is EAX, you have no clue about it, it's undecidable, and EBX is actually a yes, it's the return value of the call to G. So what you do is you combine these lattices, which is quite easy, to a big lattice. You run the MFP solution, the algorithm you've seen before for every function, and at the end you get for every function the solution of the combination of the 4 lattices. You combine them, and well, you get an overall solution, which is hopefully the return values and arguments of the corresponding functions. And yeah, that's it. Thank you for your attention.
So, about this inter and intra-procedural analysis, is it static?
Yeah, it's static.
And
everything is static.
It's performed on the assembly, yes?
In our case, yes. Technically, you can also perform it on like any kind of code.
Okay, and the results are accurate, or I mean?
Well, it finds like the in the case of the lattice, it gets to the just to the nearest point of the combination of the stuff. You know, I mean, it's only if you combine like maybe, and yes, maybe, you get yes, maybe, and hopefully that's like the best solution. It's not optimal. There are other algorithms that are, if they present you a solution, they are optimal, but it's quite okay.
Anyone else?
Yes. In this case of like the function call, for instance, is it sufficient to assume that if you write to a variable and you read after, it's an argument of the function and it's not just I mean, shouldn't you check also that it's actually used inside the function? I missed that point. Maybe there is a policy in the slide to skip.
Well, you could check. I mean, if it's a okay, if you write before and you don't use it inside the function, there's also the possibility that it is an unused argument. Okay, so we still say, okay, it's a yes. There's also the case of the saved register. In that case, well, it's of course a no, but we cancel out all the saved registers. So we assume actually that if it's not used inside the function, but set before, it's like an unused register, unused argument.
Okay.
Yeah, but it's a good point. Yeah.
What if maybe I write into a variable and I don't use it in the following code for a function, but in another code?
Or you have
Like
certain kind of
into
depth.
A, call F, call G, call H.
Well, we only consider the actual last call, and we assume that if you transfer it to certain levels, you just put it in the next function, the next function, next function. So you transfer it. Otherwise, it would be really untypical if you just grab an element from the last three functions. Usually, you only can access the stack part of the caller. Otherwise, probably violate certain compiler things. But it's a point maybe in Norway. Yeah, I mean they do crazy stuff.
Okay, anyone else wants doubts?
I have some kind of philosophical question about your lattices, because I noticed that all the lattices that you presented have a maximum, we can say, that is the contradiction thing.
Yeah.
But as far as I understand, this monotone framework usually, at least not, for what I know, is that as you go up the ordering, you should, if an element is on top of other two, it should be compatible with both. I don't know, if you have a value range analysis and you merge two ranges, what you get is the range which includes both. And in this case, you include yes and no, so okay, philosophically, okay, it's a contradiction, but what does it mean for your analysis? If you ever reach a contradiction, you say, oh, the analysis I did is wrong, or
yeah, something went wrong, actually. The contradiction is something went wrong. It's
okay.
Hopefully, the assumptions are violated.
Okay.
You should get a contradiction if the assumptions are violated. Otherwise, we made a mistake in our analysis.
So there are some. Okay. But can you make an example of a case where you violate? An assumption is violated and you get this kind of contradiction, or it's just some fail-safe thing you put inside so that you have the ascending chain relationship.
Yeah, you can of course have problems with dead code.
Okay.
So due to the dead code, you can have it's a yes, and inside of the function you have no, and later on you combine it at the very end, and you have a yes and a no, and you get a contradiction due to dead code.
Because you had that code, okay.
Yeah.
Thank you.
That might be possible.
Right. So if no one else has other doubts or questions, we shall thank our speaker again.